Chapter 11 Kinetic Theory of Gases, Section 11.1 One-dimensional velocity distribution of gas particles. Maxwell and Boltzmann proposed that the probability of a gas particle moving at a speed between Vx and Vx plus dVx is proportional to a exponential function e to the power of negative kinetic energy in the x direction over kBt. The kinetic energy is half mvx squared in this x direction. The probability of finding the particle moving at a speed within this range can be written as a times this exponential function times dVx. Again, this is exponential function of negative kinetic energy over kBt. dVx is the range, and A is the normalization factor. We can also write the probability to be the product of the probability density within the range multiplied by the range. So this f function is equal to A times this exponential function of negative kinetic energy over kBt. In case of B is the Boltzmann constant. Case of B is the gas constant over the Avogadro constant, and we have the value here. A is here to ensure the integral of this whole thing from 0 to infinity is 1. The physical meaning is simple. The probability of having a particle moving at a speed between 0 to infinity in the x direction is 100%. Again, f is the probability density function. So over here this is f. F is the normalization function multiplied by this exponential function of negative kinetic energy over kBt. Or you may view this as a Gaussian function of this Vx. You can see this Vx is squared over here. So it depends on how you view this exponential term. Now let's look at the definition of the probability density again. This f, the probability density, is equal to, well, the probability of finding the particle moving at a speed within this range and then divided by the range. That's why it's called probability density. Now if we look at the velocity instead of the speed, we'll have a different distribution of probability. Why is that? Well, if you tell me the speed is 5 meters per second, then the velocity can be positive 5 or negative 5. So somehow the probability density of having the positive 5 meters per second versus negative 5 meters per second should be the same. So we have to kind of just divide the probability density of this speed by 2, and then we'll get the corresponding probability density for this positive velocity and this negative velocity. And that's why we have a Gaussian distribution of velocity, symmetrical with respect to 0 velocity in the middle. So you can see on the left we have negative velocity, on the right we have positive velocity. Alright, and then this is symmetrical with respect to a 0 velocity in the middle. Now here we have the probability density of velocity. Maxwell and Boltzmann proposed that the probability of a gas particle moving at a speed between this range is proportional to this Gaussian function of Vx, or you can say exponential function of kinetic energy. And then over here we have the expression for probability. It's the probability density multiplied by the range. The probability density function is the probability of that range divided by the range. The SI unit of probability density is second over meter. It sounds weird, but probability is unitless. On the bottom we have a unit of meter per second. So that's why this probability density has such weird unit. Since the total probability of finding a particle within a speed between 0 and infinity should be 100%, and then we have the integral of this probability density equals 1, and the probability density is the normalization function times just normalization factor times the Gaussian function of speed. So we can solve this equation to get the normalization factor A. A is 1 over this integral. We just need to know how to integrate this Gaussian function of speed. A common strategy of simplifying an integral is via variable substitution. Somehow, if we can set q is Vx times the square root of m over 2kBt, we can simplify this Gaussian function of Vx to a much simpler Gaussian function, e to the power of negative q squared. Alright, again, let's look at this. This is mvx squared. Alright, so if we square this part, you get mv squared. On the bottom you have 2kBt, on the bottom you have 2kBt. So if you just take q squared, you get this squared, which is just this part. So again, we'll just have to make sure this integral is 100%, and we set q to be proportional to the speed. It's speed times the square root of m over 2kBt. Now we have q squared is mv squared over 2kBt, and Vx is equal to q times the square root of 2kBt over m. And now we have this integral rewritten in terms of q. This Gaussian function becomes e to the power of negative q squared. The Vx is just q times this square root of 2kBt over m. So this whole thing is just 1. Q is unitless. You can double check. This Vx is in meter per second. But this square root is going to be in second per meter. So overall, Q is unitless. I'll let you double check. M is in kilogram. kBt is in joule. So kilogram over joule. You will get second squared over meter squared, and then we take the square root of it. Q is unitless, so the lower and the upper limits of Q is 0 and infinity, alright, without any unit. And we can look up the value of this integral of a Gaussian function. It's the square root of pi over 2. You can click this website. Just download my PowerPoint file, and you can just click it. You go to Wolfram Alpha, you see this integral. It's square root of pi over 2. We can also prove this on paper, but you do need to know how to convert from Cartesian coordinates to polar coordinates. So I'm not going to talk about that in this video. Now we just use this integral being the square root of pi over 2 here. And over here we have square root of 2kBt over m, which is a constant. So we put everything here. Now we can express a as the square root of 2m over pi kBt. This is not very convenient when we do numerical calculations, because this m is the mass of one single atom or molecule in the gas phase. So I multiply the numerator and denominator by Avogadro constant. So this ends up A appears on top and the bottom. And then over here, the Avogadro constant times the mass of one atom is just the molar mass. And over here, the Avogadro constant times the Bose constant is just the ideal gas constant R. So I like to use this equation to compute A. Alright, molar mass on top times 2. On the bottom, it's just pi times R, the gas constant, times the temperature. Again, the lowercase m and uppercase m are the mass of one atom molecule versus the mass per mole such atoms or molecules. Kb is the Boltzmann constant, R is the ideal gas constant. Now we have the normalized probability density. It's over here. It looks a little complicated, but this part is simply a constant at a given temperature because the mass is constant, Kb is constant. And again, because m and the uppercase m differ by Avogadro constant, Kb and R differ by Avogadro constant, so we have this lowercase m over Kb is uppercase m over R. The uppercase m is the molar mass, so we have this function, alright, over here. Now we use hydrogen as example. If we have a hydrogen gas, the molar mass is 0.002 kilogram per mole. I'm using kilogram because this is the SI unit of mass. Gram is not the SI unit of mass. So I just compute molar mass over RT. Okay, the reason is I see molar mass over RT here, I see molar mass over RT there, so why don't we just pre-calculate molar mass over RT? It's this. Okay, it's this. Make sure you have the right units, alright? And then we have the expression of the probability density. You plug in this molar mass over RT here, and over here you get this function. You can see the unit is second over meter. I explained why that is. And you have this equation. If you integrate this over a range for speed from 0 to infinity, you should get 100%. Now let's look at the velocity distribution. The velocity over here is equal to the probability density of negative velocity, alright, because it should be symmetrical. And if you have a speed of 5 meters per second, so it's equally likely to have this particle moving towards the positive direction versus the negative direction. So these two functions are just 1/2 of the probability density of the speed. Again, for each speed, there are two possible velocities. One is positive, one is negative. Okay, either way is possible, and their probabilities are the same. You know, whether it's positive direction or negative direction, it's the same. Now we have the normalized Maxwell-Boltzmann velocity distribution function. Alright, this is also called a probability density function. Same thing, different names. Distribution function, probability density function, they are the same. Now we have this is equal to just 1/2 of the probability density of the speed. Alright, that's why you have this 2 on the bottom versus this 2 on the top. So you have this. We can also just integrate the probability density of velocity. But if you do that, the lower and upper limits are now from negative infinity to positive infinity. It's not from 0 to infinity. It's from negative infinity to positive infinity, because the velocity is signed. It can be negative. Alright, now again, let's use hydrogen as an example. We do similar calculations. We get this expression is just 1/2 of the probability density for speed. Again, lowercase m over kb is uppercase M over r. The lowercase and uppercase m are the mass of one atom or molecule versus the mass per mole particles. Kb and r are the Boltzmann constant, ideal gas constant. And make sure when you do numerical calculations, I'd recommend you to just have all those values in the SI units. For example, molar mass should be in kilogram per mole, not gram per mole.